it is not terrible, okay? Because in any case, we could not go into details. And if anyone is interested, either in the theory itself or in the applications, which are really I mean, you cannot number them, okay? You cannot number them. As I told you at the beginning, just myself, but I'm only one, okay? I have papers that go from black holes and quantum and the microwave cosmic background to muscular dystrophy, passing through the development of smart sensors for companies who live on patents, okay? Passing through, I don't remember because I have too many collaborations. And then it takes time. So, but if you are curious, I can tell you. It's not, the story doesn't finish with what I'm telling you. It hasn't even begun. Okay? We are before the beginning with what I've been telling you here. Okay? We haven't scratched the surface. But to know that there is a surface is better than not to know. Okay? So, and of course, you have your own backgrounds. You know how to do a lot of things without need of using my tools. There is so much more in the world. Okay? So I don't even want to say that this is absolutely important for your future career or whatever. Okay? You take a glimpse at something that maybe doesn't happen too often. And as my grandmother used to say, because it is a saying of my country, impara l'arte e mettila da parte, which means learn the skills and put them in a safe place. Okay? Because once you have the skills, you never know. Maybe one day. Okay? So, with this much, let us... and then what I want to say is this. I have seen some of you a little worried about the content and things, much as I try to reassure you that it will not be, the exam will be easy and so on, although it has to be done. That in the last hour, whatever I have covered now, which is short, and in the second hour, in the last hour, we may just have, for good part of it, half an hour or more, I'll see, just a free discussion between us. Okay? Now I also sit. You don't only sit. If you have questions, curiosity, or things, I try to give you my view. Okay? So, for the time being, let us continue what we started. Sivaraji, because we started late, you tell me when I have to stop. If I have to stop at 11:30, right, then I stop at 11:30. Can I have the full hour? Yes. If you like, it's not, okay? Okay, so anyways, now I continue with this part. And let me remind you quickly which was the last thing that we wrote last time. So we had this. We had that a probability density about a certain value z of some random variable at a given time t plus tau can be expressed as an integral over all possibilities of a so-called transition probability p of z at time t plus tau, given that we started in z prime at time t, okay, times the probability at time t of being in z prime, which is wz prime t dz prime. Okay? This is the probability, the elementary probability of being close to z prime at time t. Now you combine that with the transition probability and you get the probability density at time t plus tau in the point z. And this becomes a definition of P. You don't have to ask yourself how difficult it is to prove that equation. No, it's not equation, it is a definition. Okay? Oh, by the way, now that I see you, some of you, right, reminded me that in my previous class, I told you that a measurable function is a function that maps measurable sets into measurable sets, but maybe I was tired. Because it is the inverse, no? It is always the pre-image that we are interested in. So it is measurable if its inverse maps measurable sets into measurable sets. Okay, so I wanted just to say this because it was a mistake that I had. So anyway, we said things can be written in this way. Now for P, we have written an expression. Okay, after we introduced the characteristic function. Now I don't repeat the whole thing. Okay, I just go straight to what we need. We have that P of z at time t plus tau, given that it was in z prime at time t. Okay, this could be expressed as an anti-Fourier transform of the characteristic function, which is this. 1 over 2 pi integral from minus infinity to infinity for variables that are only one-dimensional of e to minus I u z minus z prime that multiplies n from 1 to infinity of iu to the n divided by n factorial, okay, of the moments of the transition probability, mn of z prime at time t with an increment tau, okay, and this has to be integrated in the Fourier variable u, du, okay, where the moments of p mn of z prime t and tau could be expressed as the integral from minus infinity to infinity of z minus z prime to the n times the probability density of which you get the moment. So P of z t plus tau given z prime at time t, okay, integrated in dz. Okay? So I think we came to this point. Now, as I told you, look, if you read the books, maybe even if you listen to some lectures, maybe they don't make clear this fact that so far we have done nothing. Okay? But we spent a lot of time in class. We have done nothing. Because we have only tautologically rewritten things. Okay? So far, we have nothing in our hands that can be used. Okay? But as Gauss, the great Gauss, used to say, to look at the same problem from a different perspective is always useful. So by rewriting things and doing nothing, we have, however, provided a different point of view on the same thing. Okay? So maybe we can use it. Yes, in this case we can use it. We are not always so lucky, okay? But sometimes we are lucky. So what do we do? In here, we have this product of P times W. Okay? Now we have an expression for P. This P was unknown before, it is unknown now, because here it is defined through Mn, which is defined through P. So if you don't know P, you don't know Mn, and you don't know this. That's why I'm telling you we did nothing. But watch out. Watch out. Let me write P times W. P of Z T plus tau, given Z prime at time t times W of Z prime at time t. This will be equal to this right-hand side multiplied by W. Okay? So it becomes 1 over 2 pi integral from minus infinity to infinity of e to minus I u z minus z prime. Now bracket. We take this inside the integral. Okay? So it becomes W of z prime t because you see here we integrate in du, okay? So I can take it inside the integral. W z prime, which goes in place of 1, plus sum in n from 1 to infinity of iu to the n divided by n factorial m n of z prime t tau that multiplies W of z prime t, okay, and all this integrated du. Okay. The W, because depends on z prime and t, can stay equally the same inside or outside the integral, doesn't make a difference, but if I write it inside the integral, it becomes more interesting. Okay? Now, in my notes, there is the explanation. I only give you the result. And you may also be aware of it, okay? Without any need that I tell you. But there is one expression of the Dirac delta function, delta of x, as a Fourier transform. Okay? 1 over 2 pi integral from minus infinity to infinity of e to the I kx dk. In which sense this is equal to this? In the sense of operators. It means that if I apply the linear operator defined with this delta of x to a certain function space, then it is the same as if I stick my function inside the integral. Okay? And what do we know about delta x? We know that its integral, that the integral of a continuous function, it has to be at least continuous. Okay? The integral of a continuous function with the measure that is delta x dx is equal to the function in point 0. Now, you think, and if you stick the function here, you get the function in point 0 if it is continuous. Okay? In my notes, in any case, there is the direct derivation. So let's come back to this, having this in mind. Because now you see, you have some stuff that you can treat as a delta function. And so, if we write W of z t plus tau, which is the thing we would like to know. What is known in this equality here. What is known is the probability at the earlier time. That you have to know, okay? Because even if I say I drop this pen and thanks to gravity it falls to the ground, that is an equality. But to know how it falls to the ground, I have to tell you what is the initial condition, how high it starts, and also if it starts from standing still, like now, or if I throw it up and then gravity pulls it down, or if I push it down. So the equation is still the same, but the initial conditions make a lot of difference. And without knowledge of the initial conditions, you cannot go anywhere. So we have to know that. But if we are lucky, we do an initial measurement, we do some initial operation, and then we know the initial situation. That is what breaks that vicious circle of going around and knowing and going from knowing nothing to knowing nothing. How do you break this vicious circle? By the knowledge of the initial condition. Because now you know something. Now you know a little. Maybe little, but with this little knowledge, maybe you can do something. Now look at this as it is written. Okay? I can express it in this way. I can express it as integral of w z prime t, which is the thing that I have inside this integral here, times the delta function evaluated at z minus z prime dz prime. Okay? Which is the first piece we have here. You see? The 1 over 2 pi integral from minus infinity to minus infinity e to the iu z minus z prime. Okay, you see, you get the delta at x. If here I stick z minus z prime, I get the delta at z minus z prime. Okay, so now I have this times this. Okay, the w inside or outside the integral makes no difference. So this is what it is. Okay. And then I have plus. Now, look at the next term. Okay? In the next term, you have n equal 1. You have n equal 1, and then you have iu. Iu to the n, iu divided by 1. You have iu. If you look at this expression here, that is the derivative of the exponential. That brings down a minus iu. But here I have a plus iu. So this thing becomes plus, but actually minus, derivative with respect to z of the integral of, here you have m1, because we are at n equal 1, so you have m1 of m1 evaluated at z prime, t, and tau, okay, times w of z prime t, okay. Now, because I have done this derivative, I'm back to have an exponential, because the exponential doesn't change when you differentiate it. It only pulls down the constant factors you have in front. So I still have a delta function. From this, that multiplies this stuff. So again, I will put a delta z minus z prime dz prime. Okay? IU, m1w. The IU, I get it by doing the derivative with a minus sign, because here there is a minus sign. So I have got the IU. All the rest is m1w, And then I have 1 over 2 pi integral of the exponential. It is a delta function, like before. Okay? So that is what you get. I just do you continue like that. The second step will have the second derivative, because you will have IU to the second power. So you bring down minus IU a second time. Minus minus gives us a plus. But now look at the structure of this integral. The structure of this integral is the product of m1 times w times the delta function. This evaluates these functions in z prime, evaluates them at z. So see what you get. You get from this w of z t, which is our initial condition, the one that should be known, what I have at time t, plus, which is a minus, d by dz. What is that? This is the moment. This is the moment that multiplies w. So you have minus d by dz m1 of z, because now we are there, t and tau, times w of z t. And the second term, well, the second term will be plus. Now you have 1/2 because you have 2 factorial, which is 2. Okay? 1/2 second derivative with respect to z. Second derivative with respect to z of what? Of m2 of z t tau that multiplies w. Now you know how to continue. Okay? Now this thing is already something. Now we are out of nothing. We have something because we have assumed that we know w at time t. But you can reach time t from time 0, so you know the initial condition. Why this is something? Because on the left-hand side you have your unknown function at time t plus tau. But on the right-hand side you have the known w. You have the known w. So if you could in some way compute m1, m2, and all the following ones, now you can get the solution that you were looking for. So the question is, can now we get a little further? And I wouldn't be here if we cannot, right? Can I, what do it? Ah, here. Beautiful. Now use the right pen, and try not to drop it continually. Pen is already selected. Okay. Now let's do something. Let us write this quantity. W of z at time t plus tau minus w of z t and divide by tau. Okay? So if I do that on the left-hand side, I have to do that on the right-hand side. if I take the limit for tau goes to 0, this is equal to limit for tau that goes to 0. Sorry, that comes after. This, of course, is equal to dw by dt evaluated at z and t. Okay? But is also equal to limit tau that goes to infinity. And now we do the same trick on the other side of sum in n that goes from 1 to infinity. Now we lose this. We lose this w because we do minus w. Okay? So sum in n from 1 to infinity of 1 over n factorial minus nth derivative with respect to z of, what have we left? We are left with mn of z, t, and tau. We have divided by tau. Okay? And we still multiply w of z and t. Okay? So now the question is if I can evaluate this limit for the things that depend on tau. If I can get some expression for the things that depend on tau, which is this ratio. It is this ratio. Now you know, the story now gets a bit involved. But if you follow, if you have any book on stochastic processes, okay, and there are many, and I told you some of them, or if you have a chance to attend a course on stochastic processes, then they will show you that for a number of interesting cases, in fact, it is possible to give an explicit expression to the limit of mn divided by tau. Okay? But this becomes, has to be treated on a case-by-case basis. You give me your stochastic process, and then we will look at the expressions of this limit. Okay? Now there is a very famous theorem by Pavula that is almost as old as I am, but not that much. 1967. Okay? So it is a fairly old theorem, but I'm quite older than that. And that gives us a very useful hand. Yes? Here? The limit goes inside. No, the rest are like constants, no? I don't know, maybe I don't understand the question. Division by tau. Ah, sorry, 0, 0. You're right. Yeah, you have to... Eraser. Ah, eraser. It doesn't care much. I do select. You're right. Must go to 0. Okay? Now, this theorem by Paula, what does it tell you? It tells you this, that this equation that is named after Kramers and Moyal it is called Kramers-Moyal expansion. Why an expansion? It is clear, right? This Kramers-Moyal expansion can only have 3 cases. Okay? That it stops at n equal 1. Because all the other terms are 0. This is the case of deterministic dynamics. Okay? If you go to the program, it says that at some point I give the connection between stochastic and deterministic. Okay, if it stops at n equal 1, you are in the deterministic case. Because what you get, I will write it later a little more explicitly, is the Liouville equation. The equation that we treated in the lecture before the last. Okay? So you are in the deterministic case. Or it stops to n equal 2. This is the case that people actually normally use, to which the so-called Fokker-Planck equation, that now I'm going to tell you what it is, belongs, or it doesn't stop. All terms will be different from 0. Okay? So this is a deterministic case. This is a stochastic case in which there is a deterministic part, something that looks like a deterministic part and an added diffusion process. And this is the most general case that nobody wants to treat because it's very complex. It is very complex. Now, in many situations, what people can do is to say, yeah, this thing goes to infinity, but if we truncate at a sufficiently large n, we get it sufficiently good. Unfortunately, it does not work that way. If you are in case 3 and you neglect some of the terms, say from high order to infinity, because you think you have got good enough, no. As time goes, probability densities can become negative. They can become negative, but probabilities cannot be negative. What is the probability that this afternoon it rains? Minus 0.5. Have you ever heard something like that? No. Negative probability is something we don't want even to think about. Okay? Please. Other 10 minutes. Yeah, but if it becomes too heavy, I'm happy to stop earlier. The only thing, I need to go to the restroom 1 second. So but I come back right away, yeah? finish a little earlier. Okay, so these three cases, 1, 2, and 3, is what the theorem of Fowler does. Now, if any of you is familiar with the notion of cumulants, of cumulant expansion of a probability, then it is the same thing. Okay? If you have a probability, you can express it in terms of its characteristic function that I gave you the other time, which is defined in terms of moments. But a more useful notion is that of cumulant. I don't have the time to go through that. If you know, good. If you don't know, never mind. Yes. Yes. Thank you. Maybe it captured anyway what I was saying. So the expansion of a probability density in terms of cumulants that are related to moments, by the way, through a formula of a famous mathematician from Turin. Again, Fa di Bruno. Okay? He has a very important formula in combinatorics and number theory. And he was from Torino. So cumulants and moments are connected to each other. Actually, Fa di Bruno wasn't the only one who had in mind that kind of formula. And so there is always a little bit of friction. You know? No, it was my formula. No, it was his formula. In any case, I think that mostly you find in the books about Fa di Bruno. And someone else gets a little angry, but like Liouville is credited for an equation that he didn't invent. At least Fa di Bruno invented his own formula. If also someone else did it, okay. So the formula says that the cumulant expansion can either stop at first, second order, or go to infinity. And it is the same thing. Okay? It is the same thing, and you could guess that it is something of that kind because the moments are related to the cumulants. But now, let us look at a case in which all this stuff easily makes sense. And that is in part implemented in the MATLAB codes that I gave you for the tutorials. Okay? It is the Langevin equation. The Langevin equation, which writes like this. You have z dot equals a certain function of z and t, h, plus another function g of z and t, times what is called the white noise, gamma of t. What are the properties of white noise? The properties of white noise are these, are that is a stochastic process. It is one of those random functions that you don't know which values they take, but you know that they have certain statistical properties. And the first property is that E expected value of gamma at any time t is equal to 0. Which is easy to obtain because whatever process that has got an average, you obtain the process that has 0 average by shifting it by the average. You subtract the average and you get 0, because average is a linear operator. Okay? And then its correlation function at different times, E of gamma at time t times gamma t prime is equal to delta. Actually, if you want to make calculation a certain way, it is 2 delta t minus t prime. This is all what you know. This is all what you know. You know that average is 0 and correlation is, as you call, delta. Is a delta correlated process. what does the second property mean? The second property is very important. And then the result is what is called the Langevin equation. Which is the most popular of continuous time stochastic processes. You find it everywhere. I use it, for instance, to describe the motion of bacteria when they search for oxygen. Okay? But people use it for almost anything that you can think at a small scale. At the scale, at the nanometric scale, at the scale of nanotechnologies. You find a lot of this. And bacteria are larger than that, but they have certain properties, okay, that also seem to be describable with a kind of Langevin equation. Of course, there are variations of this equation that are much more complex, but the idea is always this. You have some kind of systematic part in the sense that it is known what it is, and you have something that is unknown, or better, is known only at a statistical level. And if you have this delta correlation, then you are in that same field of the Langevin equation. The rest is computational difficulties, if you like. What does this thing mean? What is a correlation? Well, as the word says, it is a kind of causality connection between things. Okay? The sun shines and I get a tan. Not as much as Sivaraji does. He's a little more tan than I am, even if he doesn't get any sun. If I do, I get a little more similar. But we are still brothers, so even if not too similar. So you see, there is a correlation between the sun and the color of my skin. You understand that, right? But it's not like placing a camera on a comet, where there is more than correlation. There is causality. If I shoot the spaceship with this direction, this velocity, it will end up on the comet. While if I'm exposed to the sun, maybe I don't get the tan. Okay? It happens. It happens. But of course, this is more evident in many things. For instance, they tell you that if you smoke, you have a high probability of developing lung cancer. But the case of very old people who have been strong smokers all their life are known. And often they are brought in by tobacco producers, cigarette producers, to say, you see, it is not true. No, unfortunately, they are wrong. Because, yes, some people escapes that fate, but nevertheless, the vast majority of people get their lungs damaged, and then it is bad. And then it is bad. Okay? Same problems for living in places where there is too much pollution. It's like smoking. Say, do you smoke? No, I don't smoke. But you know, I live in a healthy environment. Maybe pollution or maybe some other reason. Could be radioactivity, which is also found in the ground or in some. Okay, so these things have to do with correlation rather than with causality. So, what is the meaning of this correlation here? The meaning is that correlations decay instantaneously. Because this thing, in a sense, in quotes, is different from zero only when t is equal to t prime. For the rest, the correlation is 0. Are there processes that are like this? Well, to a certain approximation, there are processes that are like this, processes in which the memory of what comes first is lost practically immediately. But there are many phenomena in which correlations are not lost immediately. Let me give you an example that I like, because in the science festivals in Torino that we have to attract students to the science subjects, okay? We do it throughout Europe, not only in Torino, but it's an experiment that has been done various times to impress young people and encourage them to enroll. You take water and you put flour on it. You make a pool, okay? Big pool with flour in water. Now, if you step inside the pool like this, you reach the floor immediately. But the chemical substance is starch. But if you don't do that, but you do this, you can walk on water. You can do it, okay? Go to YouTube and find the videos of people walking on water, and then they stop and they sink. Okay? Isn't that beautiful? You know what is that? That is the effect of persistence of correlations. What happens is the following. If you put your feet down slowly, there is time for this mixture of water and starch to move away from where it was. So there is time for water to forget that it was under my foot. And so I can sink. But if I do this, I don't give water the time to forget that it is here, because I hit it continually before it has forgotten. Okay? When I lift my foot, the water is still there. And when I put it down, it's still there. Now, that delta correlation corresponds to a decay of correlation that is short compared to the times in which you do your experiment. Of course, delta is a mathematical idealization. It's a mathematical idealization. There is no process in the world in which correlations decay instantaneously. But certain processes are so fast, I told you, no? Typical times of 10 to minus 12, 10 to minus 14 seconds, that for us are instantaneous. Okay? And this is the idea that Einstein had in mind when he developed this theory of the Brownian motion. Okay, where you have pollen suspended in water, and the single grains of pollen get hit by the molecules of water continually over time scales that are much shorter than the pollen reaction to those kicks. Okay, so you can imagine the pollen velocity obeys a Langevin, very simple Langevin equation that is like this. V dot equals minus gamma v, which is the application of Stokes' law for fluids. You have a viscosity that goes inside the coefficient gamma, okay? And then V dot minus gamma V gives you the effect of viscosity. Viscosity will slow you down. If you put, you know, a small object, floating object into water, you give it a push, then after a while it stops. Why? Because viscosity of the fluid subtracts its energy. Certain fluids are more viscous than others. There are viscous fluids that I like very much, like honey. Honey is much more viscous than water. Water sometimes looks to have almost no viscosity, okay? But it does. It does have. It has a small viscosity compared to honey. This is the systematic part. In this case, okay, h of zt is minus gamma v, where gamma is a constant, plus, okay, some other constant that multiplies a gamma of t with these properties. Okay? Now, is it a valid approximation? Yes, it is a valid approximation under many, many, many circumstances to a very good degree of accuracy, because the molecules of water are something like 10 to minus 16 in mass than a pollen grain. Okay? You need 10 to the 16 molecules of water to move to make the same mass of a pollen grain. And molecules move very, very fast compared to pollen. Pollen you can follow on a microscope. Okay? It was proven, this model of pollen was written in this form by Langevin following Einstein's prescriptions. And then, what do you do in a process like this? In a process like this, it makes no sense to solve the equation for each single pollen grain. Because you take this pollen grain, and in 5 minutes you find it here, another pollen grain, in 5 minutes you find it there. If you repeat the experiments tomorrow, they go in totally different things. So you learn nothing from solving directly the equation, even if you could, which is not trivial. So you treat this problem stochastically, probabilistically. And now you want to know what is the probability of finding a pollen grain within a certain region. And that takes you to this. But this sort of equation is one of the good ones. Okay? It has that, it falls in that case. And then it is an equation that can be solved. And what do we know? And this you find it explicitly computed, for instance, in the book of Risken that I mentioned to you, but also in the book of Gardiner. Risken is a book directly on the Fokker-Planck equation, which is what you get from Kramers-Moyal when you stop at 2. And Gardiner is another book that does this kind of calculations. So you can see what you prefer. Now, what we know is the following, is that for such a process like a Langevin equation, dk yes, thank you. Dk of zt is the limit that we wanted to consider. Limit tau goes to 0 of 1 over k factorial mk of z t and tau divided by tau. Okay? We need only 2, because Pavula will tell us that we stop at n equal 2. And so, if you call dk this thing, what we have for the Langevin equation is that d1 of z and t is equal to h of z and t plus g prime, the derivative of g with respect to z, g prime of z and t that multiplies G of Z and T. And D2 of Z and T is equal to G squared. So in the case of the Langevin equation for the Brownian motion, it's very simple. Okay? It is very simple because H is minus gamma V. And G is a constant. Okay? Right. G is a constant, so its derivative is 0. And then G squared will be the square of this Q. So the Fokker-Planck equation is the equation for the probability evolution of this stochastic process. Now is a soluble equation. dW by dt is equal to minus d by dz of d1 of z and t times w of z and t plus d squared by dz squared of d2 of z and t times w of z and t. And then now the equation is easy or difficult to solve depending. Did I write right? I hope. Yeah, it is a partial differential equation. It is easy or difficult depending on the D1 and D2 what they are. In this case, of course, it is very simple. So I just give you the solution, and in my notes you see how you can get it. In particular, the stationary solution to which you converge in time, and it is proven that you converge in time. So where dW by dt is 0 is the famous Maxwell-Boltzmann distribution. Okay, this is a stationary solution to which you actually converge, and its form is like this for this equation. Okay, it is probability density of velocity is our W. Okay, as a function of velocity in one dimension is square root of the mass of pollen divided by 2 pi kb, which is Boltzmann constant, times t, e to minus m v squared divided by kbt. Now this divided by kbt comes through Avogadro's number, which is the scientist from Turin, Avogadro. I would stop here even if I could go a little longer, but I think this is enough, and so we have a little more. And also in the second hour, I try to make it shorter so you have a little more time, because otherwise today is the end. Okay? If you have questions, after. In the last hour, I'll give you room to questions. Okay? See you later. What time do we reconvene, Sivaraji? 12:10. 12:05. 12:05. It is a short break, but it is for a good cause. I hope, Sivaraji, you don't mind that I called you a bit tanned. No. But we are brothers. That works? Yes. So, now we switch to a connected but relatively different case. Ah, sorry, I forgot. Let me go back just 1 second to the Fokker-Planck equation. So I told you that the Fokker-Planck equation is something like this. dw by dt equals to minus d by dz of a d1 of z and t w of z and t plus d2 by dz squared of d2 of z and t w of z and t, okay? Which can also be put in this form, and now you know what it is, minus d by dz j of z and t, where if you factor out one of the derivatives, what is left inside is j. I told you that this equation includes in itself the Liouville equation. The Liouville equation, which is for a deterministic process, is what stops here. If you go back and compare, you will see that it is the same thing. Okay? The Liouville equation is the case in which d2 equals 0. d2 is what arises from the stochastic part of the equation. So you don't have d2, which is the square of g, and g is the part that multiplies the noise. So if you don't have the noise, you have a deterministic evolution, and probabilities of deterministic evolutions are determined by the Liouville equation. Okay? So in that equation in which I wrote v dot equals minus gamma d plus gamma, apart from coefficients, okay? If you set gamma to 0, you have a deterministic process. But this process is very simple. It has a very simple solution. It has an exponential decay of the velocity. But it can also be treated probabilistically, because I can give a certain distribution of initial conditions. So you will have probabilities also in a deterministic process, which is what we did. And who decides how probability evolves? The Liouville equation. If you switch on a simple stochasticity, like many of you know, a Wiener process, then you have an extra diffusion term. Let me tell you, I already told some of you who came to my room, okay, that these kind of things are used, for instance, these days in artificial intelligence, okay, to learn how to reconstruct images and so on. Okay? And people have always considered diffusion processes easy, because it is true, they are easy. And now they realize that deterministic dynamics can also be beneficial. And like Boltzmann would say is one almost regrets to have to die before the answer is given. O immodest mortal, be your satisfaction in watching the shifting of the battle. Okay, so who lives will see. It's not important to have the final answer to all your questions. Enjoy the process. Okay? And he was using the language of a man of end of 1800s, beginning of 1900s. Today, perhaps we would use different words. But the meaning is that one. O immodest mortal. You are mortal, and still you are immodest. You want to know more than you are entitled to. Okay? Take it easy. Enjoy. So about use of deterministic or stochastic processes in artificial intelligence, maybe I don't get to see what is the end of the story. Or maybe I do. Who knows? Now, related to the issue of dynamics and probabilities, which at this point, we don't care if they are produced by deterministic processes or by stochastic processes, because we have seen that they are connected. Okay? Related to that, there is at the very beginning the notion of ergodicity. Now, as I told you in the first hour, the beginning of the first hour, we haven't even started to scratch the surface of the subjects that I'm illustrating to you. But it is better to know that there is a surface that could be scratched than not to know that the surface is there. So I will do the same thing with ergodic theory, because ergodic theory is a huge subject by itself. It arises in physics, in the field of statistical mechanics, thanks to Boltzmann. Then it gets developed, it gets different terms in the hands of Maxwell, and finally Gibbs makes it something for the mortals. Okay? Through Gibbs, the subject becomes better and better known. Because unlike Boltzmann, who used to speak in a very complicated fashion, very hard to follow, Gibbs is very linear in his ways of reasoning. Okay. So, anyway, ergodicity arises with Boltzmann within the field of statistical mechanics. What did he want to do? He wanted to describe the evolution of a gas intended not as a continuum, but as an assembly of molecules. Things are very different in our understanding. Of course, this air is made of molecules, but if I could visualize it, I would see a continuum where there are no molecules. Look at the water. Today we don't have the glass of water that I can use to show, but the same thing. You look at the water, you see that there is space is all filled. There are no holes within the water. But if water is made of molecules, then it is more holes than, what is the opposite of holes? Then it is more the empty part than the full part. Okay? Emptiness is more than what is occupied. Water is in a denser state than air. In air, the occupied volume is practically zero. Okay? And we will see, hopefully, when I finish with the Boltzmann equation, what I mean mathematically. Okay? So what was the idea? The idea was that, say you have a container, and this container is divided in two parts. And on one side of the container, you have the molecules of your gas. Now, when Boltzmann was speaking about this, people did not know whether molecules existed or not. Okay? There were people who believed that they existed, people who believed that they were only a mathematical fiction. And there was big fight. That is the question about which Boltzmann said, oh, in modus mortal, don't expect to have all answers. Okay? Do atoms exist? You need something? Yeah. Do atoms exist or don't they? You know, in the very same years when the existence of atoms had finally been proven. Okay? So there is a beautiful book by an Italian writer. It is in English. It is a biography of Boltzmann. And the subtitle is The Man Who Trusted Atoms. So he trusted atoms when the greatest scientists of the time, Oswald, Mach, they would say, no, look, atoms are a good mathematical trick, but in reality, matter is a continuum. And Boltzmann, no, it's not a matter. Regrets that has to die before the question. Near to the ICTP, where some of you have been or know about it, he committed suicide because he was under very serious depression for many years. Some people say that he committed suicide because he was frustrated with the fact that people didn't want to accept his theory. But Cercignani, the author of this book, says, no, I mean, he was under depression for many years. So he went to Italy on a holiday with one of his daughters. And then they found him hanging. So he never knew that Einstein's theory of the Brownian motion would provide the proof that atoms exist. Okay? Einstein's theory of 1905, and Boltzmann dies in 1906. Before they do the experiment in 1908, in which they prove Einstein's theory to be right, and Einstein's theory was inspired, of course, by Boltzmann. Okay? So, as I said to some of you at the break, take life easy. Okay? Enjoy the beauty. Enjoy the beauty. Even when things don't go well, there is beauty. Okay? So I like to tell this story about Boltzmann because it tells a lot about human beings, but also about science, about our field. Okay? Our field doesn't arise from people without feelings. It arises from real people. Okay? They're not just in the books. They were people who suffered and who rejoiced. So, what happens if this is not a continuum, but is a bunch of molecules? If I dig a hole in this wall, and experience tells us the molecules will move out and fill the whole container. Oh, thank you. I did not mean to have a glass of water, but since it is here. So, he wanted to have a theory of a deterministic process, because the molecules are supposed to follow deterministic rules. They bounce off each other. Okay? And continue in their motion forever. But which means that if you can go from molecules or on the left side to molecules half and half distributed, sooner or later you go back to being in only half of the volume. This is related to what Zermelo, the famous mathematician Zermelo, used a theorem by Poincaré, which I mentioned briefly in my first lecture, Poincaré recurrence theorem. Zermelo told Boltzmann, look, you cannot have what you describe. You cannot have what you describe. You cannot have that a gas goes from left to fill the whole thing and remain like that if your molecules obey time reversal invariant equations of motion, because Poincaré proves that you will go back. So your model of atoms doesn't work. There was another objection to Boltzmann. So this was raised by Zermelo. Okay, the one of the axiom, very famous mathematician, very smart. That was raised by Le Schmidt. Who was an old friend of Boltzmann, a physicist rather than a mathematician. And he also had one objection to what Boltzmann was saying, because he said, look, if instead of this bunch of molecules, say with certain velocities, you take the same bunch of molecules with the opposite velocities, which is possible, rather than going to fill the whole container, you will squeeze even more. And that is also allowed. It's only a choice of initial conditions. So Boltzmann was to face this quite challenging objections that they go by the name of paradoxes, Zermelo paradox and Le Schmidt paradox. And then basically he creates the field of statistical mechanics, which recently a very, very important scientist, one of the top neuroscientists in the world, Jim Hudspeth from Rockefeller University, that I'm going to visit next month. He told me, if you know statistical mechanics, he's a mathematician, but he knows a lot of both. If you know statistical mechanics, you know everything. I told him, Jim, he's 80 years old. Jim, you know, knowing statistical mechanics, because he wanted to compliment me, okay? He's not knowing everything. He's having some tools that everybody wants to use. So Boltzmann, in practice, although there were previous things, okay, Bernoulli, Fourier, the Italian Cantoni, you know, many others who had already done a lot in the direction of connecting statistics and mechanics. But Boltzmann, at this point, makes it plain. Okay? A deterministic process, which is chaotic in some sense, okay, will behave as an irreversible process even if all the actors involved obey time reversal invariance equations of motion. Okay? You can see that these days, after a lot of fighting and a lot of study, a billiard table with two balls in it. And these balls are moving, bouncing off the walls. Now, for a short time, you can neglect friction. But also, these days, you can do experiments with what are called cold atoms. a very microscopic level, just by manipulating atoms. Now I give you this picture at the time t1, and I give you this other picture at the time t2. Can you tell me which picture has been taken first? Is t1 larger or smaller than t2? What do you think? You can guess whatever you like. You don't do any mortal sin. You will be spared if you don't get the right answer. Or what should you tell me in response to my question? Am I asking a fair question? Again?
T1 is larger.
You say that T1 is larger, so we have an ordering like this. So this comes first and this comes after. Any other? Again?
Anything is possible.
Anything is possible. This is another guess. Now you see, time reversal invariance means what you just said. That you could have had the initial velocities oriented like this, and then this comes answer incorrect. No, it is not incorrect, because whoever told us the molecules have to obey time reversal invariant equations? We don't know. It is our assumption. And only in time, and repeating experiences and calculations, so and so and so and so, we have found that it is a good mathematical representation of what we have seen so far to tell the molecules that constitute a gas obey time reversal invariant equations. But if tomorrow Professor Sivaraji does an experiment that disproves this statement, then we change the theory. Okay? So I'm not telling you that this answer is wrong. I'm telling you that within our mathematical models, this and this are equivalent. But these are mathematical models. Is that reality? That's a different question. Now I'll give you two different pictures. And now again, this is T1 and this is T2. And what I tell you is that you go from one to the other through a spontaneous process. Now, I'm not the one who takes the balls and puts them here, there, okay? I just give an initial impulse to the balls, and now I ask you if T1 is larger or smaller than T2. What would you say? The equations of motion are the same. Okay? Still balls bouncing off each other. What would you say? T1 is larger or smaller than T2? No, nobody wants to answer. Again? T2 is larger. Why do you say that T2 is larger?
I think it's a fluid, right? It's a fluid, so the particle will not be so close for a long time. It will be scattered. Go away from it.
So this, because we don't have too much time, so I have to continue. You see, it's enough I kick one of the balls, and I will have, okay? And then they will spread. While if I want to go from here to here, I have to aim so exceedingly accurately each single ball. This, the second experiment, I think that even with today's technology is not possible. Even with present day technology. Because the dynamics are chaotic. Okay? And then here you have an exponential of 15 times something. Or an accuracy that has to be e to minus 15 and something else. It goes beyond our technological abilities, okay? So, in this case, it is fairly natural to think that T1 is smaller than T2. Then again, we can always argue that if you are good enough, you could do the opposite, yes. But suppose that you watch a movie in which particles go from this situation to this, and another movie in which particles go from this to this, I can assure you that you will find going from here to here fairly unnatural. Why? If the equations of motion are the same, time reversal invariant, why? This is the thing which Boltzmann, developing ergodic theory, had to fight somehow. Why? The difference is statistical. Here there are many balls, and here there are few. So, with the same deterministic equations, you can have something that looks like a stochastic process, because this goes from order to disordered, from order to random, or a very deterministic process that allows you to put a camera on a comet. The laws are the same, but the effect is totally different. Now, that thing is paradigmatic of all standard things that we have. Going from here to here would be if you have a hot and a cold body, that heat goes from the cold body to the hot body. You never see that in your daily life. But these days, we see it in nanotechnologies, for instance. These days, we can have that heat goes the opposite way. Why? Because we go down to small systems in which going forward or going backward in time makes no difference. Okay? So, this to give you an idea of where we are. Then ergodic theory comes out of this physical description and becomes a very thick branch of mathematics that is called ergodic theory, and that combines measure theory and dynamical systems, which is what I have tried to do in my course. Okay? So, after so much talk, let's write something that looks more precise. So to define ergodicity, we have to do this. We have to have a dynamical system, which means a manifold, M, but in the end, a phase space where things move. We need to have some dynamics on this M, continuous or discrete. And then we need to have an invariant measure, mu. Invariant means, as we said at this point quite long ago, means that the probability that it represents does not change under the application of the dynamics. Okay? Things are moved around in phase space, but the probability remains distributed in the same way. And now there are 4 properties of a dynamical system like that can be proven to be equivalent. A system like that can be proven to be equivalent. From one you prove the other, from one you prove the second, from the second you prove the third, from the third you prove the fourth, from the fourth you prove the first. Okay? Now, if you want a good book about this stuff, the mathematical theory, then that is by Ricardo Magnet. But there are many. We have that O bar of x, which is equal to limit t goes to infinity 1 over t integral from 0 to t of O computed along a trajectory starting at x is equal to the expected value with respect to mu. Now, I think we already did this question in the first class. Now, this thing cannot be true in general for all x, because this depends on x, and this does not depend on x. So we have to say mu almost every x in M. Okay? This is the first property, E1. Second property. It says that for every measurable set in our sigma algebra, we have that the residence time fraction of a trajectory that starts at x is equal to mu of a. Again, here there is no dependence on x. So we have to say mu almost every x, where tau a is equal to limit t to infinity of 1 over t integral from 0 to t of the characteristic function chi a along the trajectory ds. So what is this? This is the average amount of time that you spend inside the set A. The average amount of time that you spend inside the set A has to be equal to the measure of A, with an exception set of 0 measure. No, I'm sorry, maybe I drank too much water this morning. Can you wait a second?
I'll give you the load. Good. Next week.
Yes.
You
Yes.
time. Yeah, one maths one, another.
You also nice one. But I mean, you very famous guy, different system. I will come to you.
Yeah.
Now, property 3. E3. There are no non-trivial non-trivial integrals of motion which integrals of motion or constants of motion are those quantities that they don't change along a trajectory. Okay? It's like if you go to a mountain, they are like level sets. If you know, rather than climbing the mountain, you go around and remain at the same altitude, then the altitude is a constant of motion. It does not change. Of course, it's not constant because you are going around. Okay? But the altitude remains the same. So there are no non-trivial integrals of motion. It means that all those that exist are trivial. Trivial means that they are constants in the sense of Lebesgue, apart from a set of zero measure. Okay? So, in formula is this. If O phi t x equals O of x for all t and mu almost every x, O integrable, okay, it means L1, okay? O integrable. So if you have this situation, then you have that O of x is a constant Ko independent of x apart from this for the set of zero measure. Mu almost every x. So if you are a constant of motion, if you are an integral of motion, then you are a constant. In the sense of Lebesgue, you are a constant. You belong to the equivalence classes of all functions that are equal apart the set of zero measure. E4 says this is a bit more mathematically abstract, but it is useful for proofs of theorems. E4 says that the dynamical system is metrically indecomposable. Is metrically indecomposable, which means if A is an invariant set equals phi t A for all t, then either mu of A equals 1 or mu of A equals 0. It is called indecomposable, okay, because you see that any point in A has to remain within A, and every point outside has to remain outside. And so A, a set of full probability 1, is explored by single trajectory. And that single trajectory keeps it together. It is indecomposable. If you break it, you break also the path of some trajectory. Okay? Now, lemma. EI are equivalent. Okay? Which means that if you can prove the validity of one, then all the others hold. Or if you assume that one holds, then all the other follows. Some of these equivalences are fairly quick to be seen, because I told you many times of the density of simple functions in L1 space. So the first two, okay, get the equivalence using that property, because with characteristic functions, linear combinations of them, you can build any function of L1 arbitrarily close in the L1 norm. So going from here, you can go up there by a density argument, density in L1. Okay? And you continue like that. The usual thing, I think, is to go E1 implies E2, which implies E3, and then E4, I don't remember well the sequence. I have to think. Maybe it is in my notes, which I wrote, but I don't remember always everything. Okay? This is the notion of ergodicity. Now, if you combine E3, yes, if you combine E3 with E1, you will understand why Boltzmann found that this notion was suitable for his problem. Okay? Because suppose that there are no non-trivial integrals of motion. Then, if you want a probability measure that is invariant and that has got a density, I like the other one better. If I want to have d mu of x equal a certain probability density f of x dx, then f is a function. I want it to be, if that is to be invariant, then f should not change in time. Then it will end up within the integrals of motion. But then, well, here the reasoning is a little longer, but then if that is an integral of motion and the dynamics are Hamiltonian, as we said earlier, which implies that there is no contraction or expansion of volumes, then the consequence through E3 is that F is constant almost mu almost everywhere, which means the uniform distribution. Okay, so if your system happens to be ergodic, and it is ergodic if one of these properties is verified, okay? Definition. M phi mu is ergodic if EI holds, whichever it is. Okay? So if your dynamics happens to be ergodic and your dynamics are Hamiltonian, then there is only a distribution of probability that is invariant, and it is the uniform one. Okay? And so your gas has to be distributed uniformly over the space. And it is invariant and it doesn't go back. Okay? This is the notion of ergodicity. Some of you already had in mind this notion. I tell you that there are many theorems related to this notion. I also tell you that if you give me a generic dynamical system, typically it's pretty hard to prove that it is ergodic. Even if it is ergodic, it is pretty hard to prove that it is. Of course, there are cases in which you can prove it, but typically they refer to very simple dynamics. So let me show you one kind of ergodic dynamics. Suppose we are in the case in which the invariant probability is precisely the Lebesgue measure, dx. Then this E2, what does it mean? It means that every trajectory will spend some time in any open set of positive measure. So if my measure is dx, it means that if I take any open set, places anywhere you like, your trajectory will go through it and will spend a certain fraction of time in that set that is equal to the measure of that set. So that means that trajectories are dense in the phase space. Now I'll give you one example. And the example is this. You take a phase space which is a square that could be seen as a torus that has been cut. Okay, so it produces periodic boundary conditions. And I take a certain number of points in a certain region. And then I say that these points move with constant speed, with constant velocity along space. Okay? So they move parallel to each other. Now, because of periodic boundaries, when the points go out this way, they come back this other way. And they continue. Now, if the angle that trajectories make with respect to the horizontal are rational with respect to pi, if alpha is equal to the ratio of two integers times pi, all trajectories will eventually come back to where they started, and you will be on a periodic orbit. Because you go q times around one direction, and you close in that direction, maybe you have not closed in the other one, but there is a common multiple of these two that take you back in both directions, both in x and y. And so you come back, and you close your trajectory. You are on a periodic orbit. So if alpha is like this, you are not ergodic, because a trajectory doesn't go everywhere. It goes only along the points of the periodic orbit. But if alpha is not rational with respect to pi, then there is no multiple of return times that is common both to x and y. So trajectories don't close. But if trajectories don't close and you cut a line through this space, you will see that when they go out, they come back at a certain distance from each other. Then they go out. They cannot return to the point where they started, so they come back closer. They come back to another point. Okay? And they cover this by steps of a fixed distance because the slope is fixed. So if they do this, they have to accumulate everywhere in space. And so trajectories will feel densely this segment. And then, of course, every segment will be filled densely. Trajectories will be dense. So simple dynamics like this are ergodic. If that angle is like that. But this property was not considered good enough because the points don't spread to fill the space. They don't spread to fill the space. So people have invented another notion that is stronger than ergodicity, that is called mixing. I give you the definition of mixing, and then I stop, as I was required by Professor Sivaraj. A mixing, unlike ergodicity, but similarly, is defined by two properties. Which are these. If I find them, otherwise I go by heart. Well, no. Let me give you the main theorem of ergodicity. It is this one. And then mixing, I tell you something in the afternoon. Now, if I go back, you see that the first property is the equality of time averages and phase space averages. Let's see what can be proven. This theorem dates back to 1932, I think. It's due to Birkhoff, who made von Neumann very angry because von Neumann had the chance to tell Birkhoff that he had in mind something, a proof in L2, and Birkhoff developed for L1, and then it became his theorem. Okay? So it is this. What we can prove is this. Is Birkhoff ergodic theorem. Birkhoff ergodic theorem. What does it say? It says that take a dynamical system m phi mu. I give you in the notes also the proof of this theorem. It's fairly long, okay? But it is nice. It's very instructive. Take a dynamical system like that. Then you have this. A. For f in L1 of m and mu, what you have is that time averages exist mu almost every x. B, f in LP of m mu, okay, with 1 less or equal than p less than infinity, implies that not only the time average exists, but f time average belongs to LP. Now, you remember that the time average depends on the initial condition x. Okay? So it is a function. C. It also converges in the norm. Lim, say for discrete dynamics, lim n goes to infinity of the p norm of f bar minus some 1 over n, some in I that goes from 0 to n minus 1 of f composed with the dynamics phi I, this norm goes to 0. So the time average exists. It is an LP function, and the partial sums, or partial integrals if you are in a continuum, converge in the P norm. Moreover, the time average is a constant of motion. F bar phi x equals f bar of x. Because if you move forward some steps, you still have to average over an infinite amount of steps, so it will make no difference. That part of the theorem is easy to prove. C, if f is in LP of m and mu, always with 1 less or equal than p less than infinity, then unfortunately what you can prove is not good enough. Then what you have is that the phase space average integral over m of f d mu, which is the phase space average, okay, what I called the E mu of f, I think, okay, is equal to integral over m of f bar d mu, not equal to f bar. Okay? So it is a very weak result compared to what Boltzmann wanted. And you cannot go much beyond this, although it is old, unless you choose very special dynamical systems that can be proven to really be ergodic in the sense that I have shown before. So life is hard. But there would be many ways out. But I think we have to leave that for when you are older, and I'm older too. For today, this is enough. Thank you. Sorry, you will be busy while I go to lunch. Then I come back. I hope you forgive me.
Any questions?
the last few things that is useful to know that exist. There will be many more, and as I told you, in just one of the screens, there's the beginning of 30 hours class, just in one of them. So, okay, fair enough? Okay, so I know talking to you, I realize that many of you already have a very strong mathematical background, but on different subjects. Okay? So it's not there is nothing bad not to know the things that I do for a living. Because you already know a lot more that I don't. So I tell you my story, on which I've been working for quite some time, and then I hope one day you find it useful. At least you find pleasing that you have attended these classes. Certainly I am happy to have been with you along this week. Now, this is the last lecture hour, and then we have tutorial. So also during the tutorial, maybe we continue with a relaxed conversation of things, like while you look at my little MATLAB codes. But to conclude as much as possible the theoretical part, let me tell you about that other property that I mentioned, which is mixing. Now, mixing is a stronger property than ergodicity. Okay? Now, I still have to define it, but mixing implies ergodicity. Okay? Now, the example that I drew at the board earlier, which I repeat, is ergodic, is an ergodic dynamics. But is not satisfactory from Boltzmann's point of view. Because Boltzmann wanted to see that the gas expands to fill the whole volume, while what I have drawn does not expand. It remains within a certain region. Okay? At any time, thanks to periodic boundaries, it goes out and then comes back. Okay? And the initial ball of points remains an initial ball. It never spreads to fill the space. Okay? So people thought that you need something stronger than ergodicity, or say something different, then it was proven to be stronger than ergodicity, and it is this mixing. Now, in this case, there are two equivalent properties, M1 and M2. Now, it says that M1, for every two subsets A and B in the sigma algebra, we have this property. Limit time goes to infinity of measure of phi minus Ta intersects with B equals mu of A times mu of B. This is 1. Because T can be shifted, okay, this is also equal to limit time goes to infinity of mu of A intersected with phi tb. Okay? This property M1, this is M1. Property M2. M2 says that for every two observables O and P belonging to L2 of M and mu, we have the following. Again, limit t goes to infinity of integral over M of O composed with a time evolution that multiplies P d mu equals integral over M of O d mu times integral over M of P d mu, which can also be written like this with expectation values. Limit t goes to infinity of expectation with respect to mu of O composed with phi t times P d mu minus integral here. I wrote the expectation, I should have not written the integral. Expectation of O composed with phi t times P minus product of expectations of O times expectation of P is equal to 0. The integrals are expectations, okay, because they are integrals with respect to the probability measure. So in this case, I have the expectation of the observable O composed with phi times P. And here I have the expectation of O and the expectation of P. So this is a little more compact, but it's the same thing. You can already see that these things are equivalent because you can go using the usual story of simple functions being dense in L1 with a finite measure. L2 is smaller than L1. So if they are dense in L1, they are dense also in L2. Okay? So going from above to below is very quick. And raising up is even quicker. What is the difference between ergodicity, which is something like this, that is realized when this angle is irrational with respect to pi, so that trajectories do not close, and then they travel densely through the space. Okay, this is just ergodicity, and mixing. Well, the difference, we can get it from this representation, from M1. Then I will say something about M2. So because the limit has to be equal to the product of these two measures, if you take time large enough, this and this are approximately equal. And if you don't think that they are equal enough, you just take a longer time. So what I can write is this, is that mu, let me use this equality here. Mu of which is better that I take? Let me see. Yes. Mu of B will be approximately equal, but with a plus or minus epsilon as small as you like. Mu of B will be equal to mu of A intersect phi TB divided by mu of A. Okay? What does this mean if it is realized? It means that, unlike this case, say if here I have B and I place A anywhere else where the measure of A is different from 0, because otherwise I cannot divide. So if I take an A in any other place in the space, okay, as long as its measure is positive, and if the invariant measure is the one of Hamiltonian systems, which is the Lebesgue measure, which is just dx, x vector, okay, if you like, in this case dx dy, horizontal and vertical, okay? It says that if I evolve B in time, at some point a part of B will be inside A. Because the intersection divided by this constant is equal to the measure of B. Think carefully. Whatever A I take, say I take this other one, inside this new A, there is a fraction of B which is equal to which fraction of the full space B is. Because the fraction of the evolved thing inside A is equal to the fraction that B is of the whole. So this means that as time goes, you will have a piece of B everywhere. So B, that was this small ball at the beginning, has to go everywhere. Now, interesting enough, that can be done also preserving volumes. That can be done preserving volumes with a Hamiltonian mixing dynamics, preserves volumes. So what should happen is something like this. Is that I start with a ball of points, and then as time goes, this ball of points gets stretched, filamented in such a way that it reaches everywhere. The volume has not changed. So it has to get thin and ramified. Okay? And this is mixing. Now this corresponds, at least visually better, to the idea that Boltzmann had. But now, at the end of the previous class, I told you that these mathematical objects, much as they are very interesting as mathematical objects, they can hardly be applied in many not that mathematically abstract applications. In particular to physics, but then physics is the world in which most of mathematics can be used. The vast majority of mathematical tools are already used, if not all of them, in physics. Okay? So it is good to know this stuff, because this stuff leads to a lot of rigorous results about which you are sure that what you prove is going to be true. While other notion of ergodicity, let's stay with the weaker one, okay, ergodicity. But this is an important result, so I have to highlight. Okay, this is a theorem. If a dynamical system is mixing, then it is ergodic. This notion is also used for stochastic processes with the notion E1 for ergodicity. Okay, in stochastic processes you would use this, and M2 for mixing in stochastic processes. Because expectations, you have subsets of phase space you don't have in a stochastic process. But expectations you have in a stochastic process. Okay? And time averages and expectations you have also in stochastic processes. Okay? So these notions are found not only in deterministic dynamics but also in stochastic dynamics. This is the representation of things that spread in phase space. But this notion is more general. And the quantity that you have here is called a correlation function of the observable O MP. And it is a function of time, okay? Because you have time here. Now, the correlation of observable O and P decay in time to 0 if the system is mixing. What does it mean? You remember walking on water? It means that if you give me enough time, you sink. Okay? Correlation of the molecules of water under my feet get gradually lost. They forget that they were under my feet. They move away, and I go down. Okay? Or correlation between the initial condition of the weather today and the weather 2 weeks from now, that is also lost. Okay? That is also lost. 2 weeks from now, the weather is uncorrelated to what it was today. You know, many years ago, when these things were not completely understood, there was a flood in the valley, in the Mississippi, in the US, where there were a lot of cattle, okay, grazing and being fed to feed the humans. And then the weather forecast predicted that weather would be good, no problem. Then it so happened that, on the contrary, it rained so much that there was flood and a lot of livestock was lost. Big deal. I think that the people in charge of the weather forecasts were fired. So you are incompetent. We have had such a big financial damage because of that. Okay? Time passed, and they realized that the people of the weather forecast had done nothing wrong. So what was the problem? The problem is that the weather is a chaotic system. Chaotic systems forget decorrelate in time. Okay? The fastest decorrelation is the one that we have seen this morning, the one of the Wiener process, or the white noise. The correlation decays instantaneously. For weather, correlations decay in the order of 1 week, 10 days. Now, you can see this way. It is because sorry, you can see this way. Memory has been lost because what was in a given spot, now there is a little bit everywhere. It doesn't matter that things started here. They could have started here, they could have started here, doesn't matter. There will be a little bit everywhere, okay? This is what it means. Okay. There is a problem, even if things make sense. The problem is that all these things are in phase space. If you have deterministic dynamics, they are in phase space. And phase space is not a natural space. Okay? Phase space is very, very difficult even to imagine what it is. For instance, when I drew my billiard this morning with two balls, the real space is two-dimensional, no? The balls move in a two-dimensional space. We understand what it means to have balls uniformly distributed in the two-dimensional space. If you have two, you cannot distribute them uniformly. Okay? But if you have many, okay, then this is more or less a uniform distribution, right? If you have more, you can make it more uniform. So the idea of uniformity comes out when you have many particles, not just two. Now, and in real space. What is phase space? Phase space, for this case here, is two coordinates for one ball, two coordinates for the other ball. We already have a four-dimensional space, which already we cannot represent easily. Plus, you have two components of the velocities. So you have 8. So 2D is real, and 8-dimensional is phase space. The ergodic and mixing notions, they refer to this 8-dimensional space. Incidentally, these have been proven in the 80s by some of my older than me. I think there are people older than me, friends, like Leonid Bunimovic, who is an emeritus professor at Georgia Tech. This has been proven to be mixing. So you know what it means. It means that you give me time and probability will become uniform in the 8-dimensional phase space. So this goes to uniform probability. Because it is mixing. Now I tell you, to prove that this thing is mixing is a task. It's not simple. And this Leonid Bunimovic, you know, his PhD thesis was overlooked by Professor Kolmogorov. I don't know if you heard Kolmogorov. Okay? He's one of the top mathematicians of all times. He was very sick, but when Bunimovic presented his thesis, he wanted to be present because he said, Bunimovic has an important result. It wasn't this. This came even later. Okay? Now look at this. Sorry. So probability becomes uniform, but mass remains non-uniform. You agree, right? With 2 balls, you cannot fill uniformly your space. You remember when I told you initially that if I throw you a stone, I may hurt you. If I throw you probability, it doesn't, because the 2 things are totally different. This is one way of seeing that they are totally different. However, and with this, I open the door to the Boltzmann equation, which is the last thing that I'm going to tell you. Yeah, so we have a little bit of time for discussing things. But look, remember what we said at the end of the previous hour. In here, you cannot say what is the sequence of time, because the 2 balls are like this, or they are in reverse order. Could be both. Could be both. While here, if balls are all together to form like a triangular structure, or are like this, you know that it is totally unlikely that you go from a disordered situation and spontaneously you form a triangular structure. Impossible, not against the laws of physics, because the laws of physics here are the same as there. Not impossible in principle, but impossible in practice. It is the same as saying that if you go from this disordered situation to an ordered situation, it's like to say that you have a hot and a cold body. Look at this heater. Okay? It is close to me, the one who doesn't need it. I'm sorry, because for me it is not cold. But I hope you get something also in your direction. Now you feel better, right? I just turn it by 20 degrees. It would be going from the disordered situation to the ordered situation. It would mean that I, who am not at the temperature of the heater, because that is still hotter than me, that touching it, I get colder and that gets hotter. That is what it means going from disorder to order. In our world, in the world of our daily life, that doesn't happen. The cold body gives heat, the hot body gives heat to the cold body, so that they reach an equilibrium where they're even. At least, if there isn't justice in this world, there is justice in physics. Okay? We are going towards a uniform where everyone is equal and has equal rights. Now, this is just one instance of these many physical situations in which equilibrium, even the word implies that. Equilibrium is something even. So going from compact ordered situation to disordered situation is fine, because this makes space even, okay, in its properties, all the same everywhere. Now look at this. In here, for the same reason that the dynamics are mixing, the two-dimensional real situation implies that mass goes uniform. And now with Boltzmann we will see that it does more and more if the number of particles is larger and larger. And so now you understand why in our world, in our daily life, we never see the steam from the pot where you are cooking some of your beautiful Indian dishes, you know, that comes out, smells. You never see that going back into the pot, okay? Because warming up, it has to come up and fill the room. Why? Well, because the droplets of that steam coming out are very many. Are very many. Okay? So 2D real, or in our world 3-dimensional, mass goes uniform. But because the laws of physics are the same, also phase says that probability goes uniform. In this case, because particles are many, what happens to probability happens also to mass. But how terribly complicated is the phase space of this system? You see, they are both 2-dimensional in real space, but now count. Each of this ball has got 4 coordinates, 2 positions and 2 velocities. Now the balls are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, 32, 64. This space is 64-dimensional. Can you imagine? Can you just imagine a 64-dimensional space? Well, if you can, please come to me and explain, because I cannot imagine it. I know mathematically how I can represent it through sections. I go from 64 to 63, and then from 63 to 62, and continue like that, okay, till I have given a full representation. But now try to put everything together. Okay, how can you represent a 4-dimensional, a sphere in 4 dimensions? A sphere in 4 dimensions, you can imagine a movie, right? So, and it is an extension of this notion. Here you have time, and here you have you think, okay? So in the past, you see nothing. Then time passes, you see 1 point. Then time passes, in here you will see a segment. In 3 dimensions, you would see a disk. In 4 dimensions, you would see a sphere. So let's stay in 4 dimensions, okay? Space is 3-dimensional, and, okay? So you go from, you see nothing, 1 point becomes a little sphere. The sphere grows, becomes larger and larger. It is a 3-dimensional sphere. Then it becomes smaller, 1 point, nothing, okay? This is a sphere in 4 dimensions. Now try to do a sphere in 64 dimensions. Okay? So I know conceptually I can do it. So in any case, it's just to tell you that phase space is quite a terrible thing. But if it is the phase space of a large number of particles, what happens to probabilities under proper conditions happens to mass. And so you can speak of probability and of mass as practically identified. This is the Boltzmann equation, and with this I conclude. Okay? Let me tell you how you can get to the Boltzmann equation. There are, in my notes, 2 ways of deriving the Boltzmann equation. One is the probabilistic way, that to you. Okay? There is a more concrete, more physical way of deriving it. But in the end, we get, under the proper limits, to the same equation. The same equation for probability will be the same equation for mass. And the reason is here. under certain conditions, mass and probability can be identified. So we start with this. In the phase space point gamma at time t. Okay? This will be if we have hard, I cannot give you all the details, okay, because that becomes long. But if you have hard spheres, which is a good representation of the molecules of gases like argon, for instance. If you have hard spheres of mass equal to 1, okay, then this probability density in the 2D n dimensional space, okay, so gamma belongs to R to the 2D n, where D are the dimensions. In this case, dimension is 2. 2 means twice, and n means the number of particles. For a rarefied gas in a cubic centimeter, n is 10 to the 19. It's quite more than 64. So this will be a function f and n. It means out of n particles, I look at n particles, so I look at all of them. Position of first, a momentum of first, dot, dot, dot. Position of last, momentum of last, and time. Okay? It is a function like this. Now, the Liouville equation, which I gave you in a general form, in this case takes this specific form, which is this. It is df nn by dt plus, I take things on the other side of the equal, plus some overall particles, I from 1 to n, of pi scalar gradient with respect to the position of ith particle of f n n is equal to 0. Okay? This is what the Liouville equation is. Now you understand, right, that hope to solve this solution is fairly 0. Because how can you solve a solution in a space with so many dimensions? In concretely, okay? Mathematically, we write the equation like mathematically I write 10 to the 19. But you know that I would never be able to count up to 10 to the 19, right? So one thing is to write and one thing is to be concrete. In any case, this is the probability density in this space, and as we have derived earlier on, in this specific case of hard spheres of mass 1, this is how you write it. Now you understand the reason of the notation that I use. Because I don't want to look at all particles. There are too many. Okay? So let me simplify the problem. Let me take the probability density of S particles out of N. Okay? Then this will be a function of Q1, P1, semicolon, dot, 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 semicolon, QS, PS, T. What is this? This is the marginal over all the other particles in probabilistic terms. Or, if you want, is a projection of this Fnn on the lower dimensional space of the S particles. Okay? This space will be 2ds dimensional instead of 2dn. And it is like this. You integrate in dq s plus 1 dp s plus 1 dot 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 dqn dpn of our fn n, which was of q1 up to pn n time. Okay? I have integrated out all the coordinates and momenta of the phase space distribution. And I have what in probability is called the marginal distribution, or this is a projection. It is a projection in a lower dimensional space. Now, if you do this integral that defines f and s in here, okay, if you integrate, you do this integral here, in dq s plus 1 dot 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 dpn, okay, if you integrate this, then what do you get? Well, you take the derivative out of the integral, okay, and you take the integral inside here, and you get this equation. You get dfns by dt plus sum in I from 1 to s of pi scalar product with the gradient of the coordinates qi of fns. But this is not equal to 0. You see, for the Liouville equation, it was equal to 0. But if you integrate and you stop at s, because you are looking at s in this summation, if you do the calculations, and they're not trivial, but they're possible, and you find them in the beautiful books by Cercignani, a very big expert of Boltzmann equation from Milan, who died now already a certain number of years ago, more than 10 years ago, I think. The book is called The Boltzmann Equation and Its Applications. This is a thick book and very deep. So you can see all the calculations, is that you will have that this thing is a certain function fs of what? Now, of what is the interesting thing? Of fn s plus 1 and fn s plus 1 prime where prime means the distribution of particles before they collide. Prime means the distribution of particles before they collide. After they collide, the distribution changes because the velocities change. Okay? And so you have another distribution after they have collided. Okay? This takes a little bit of work, you have to believe me. But conceptually, the thing is not too mysterious. What has happened is this, is that you want to know what happens to S particles, you have to know how they interact with particle S plus 1. Because you are neglecting particle S plus 1, but particle S plus 1 will give a contribution to the behavior of the S particles. It will hit one of the S particles. You want to know what happens to particle S plus 1 then? What is the implication? If you want to know about particle S plus 1, you need to know about particle S plus 2. You want to know about particle S plus 2, you need to know about particle S plus 3. in the US they say there is no free lunch. Okay, much I had a lot of free lunch here, very beautiful food. And I'm very grateful for that. So this equation up to n was impossible, but it had equal to 0 because all particles were already included. Here, you want to gain something, you have to pay something. And in the end, what you pay is equal to what you wanted to gain. This equation is not closed. Okay? So now Boltzmann comes one day. In fact, this stuff is all much later than Boltzmann. Boltzmann had first done what I'm going to show you now. Boltzmann says, but look, let me consider S equal 1. And in a minute I tell you why. Then if you do all the calculations correctly, now you have only 1p, gradient with respect to only 1q of fn1, it will be equal to. What kind of interactions can hard spheres have? The only interactions that they can have is collisions with each other. Okay? They are hard balls. When they don't touch, there is no interaction. And when they touch, they bounce off each other, like the balls in a billiard. So, my particle 1 can collide with the remaining n-1 particles. And each of these particles has a cross-section, which is sigma squared, which is the area the particle 1 sees of the other particles. If you want to hit this, you have to be with the right parameter. If you are too much to the left or too much to the right, you don't hit it. So sigma squared is the area of the other, of the n-1 parts that you can hit. So you have proportionality to how many particles you can hit and their cross-section. And now you have an integral over all possible velocities, okay, which are in R3, if we are in a three-dimensional space. Then you have over all possible angles of approach, so it is a half sphere of directions through which two particles can approach each other. And then you have Fn2, because such is life, as is written there. Fn2 prime minus Fn2. And then you have the direction of approach, which is P minus P star, where P is the P of my particle 1 and P star is the momentum of one of the other ones. P minus P star, scalar product with the direction of approach between the two particles, that n is a unit vector in the direction joining the centers of two particles. And you integrate over the velocities of all other particles and over all directions. You need only half a sphere because, okay, for symmetry. Now this is still not a closed equation, so still you cannot solve it. But Boltzmann says, look, if particles are sufficiently many, and if the dynamics are sufficiently chaotic, in his days chaos meant something totally different, okay? Chaos, as I described in dynamical system theory, as the rate of expansion of distances in phase space. That is a modern notion. The term chaos was invented by Jim York from Maryland University, another now very old professor, but I think he's still alive. He invented the word chaos in the 80s, early 80s, and then it became popular everywhere. And here in India, there is so many people working on chaos. Okay? Well, it is working on dynamical systems with a specific property, positive, at least one positive Lyapunov exponent. In Boltzmann's days, the term didn't mean that. The term meant what he meant it to be, and he meant this. Let us say that Fn2, which will be of Q and P, Q star and P star, time t, can be factorized as Fn1 of Qp t times Fn1 of Q star, P star, and T. This is what is called in German Stoß-Hallan-Satz, because he spoke German, being Austrian, which means the hypothesis of tossing dice, okay? The hypothesis of chance. What is written here? Something very similar to what is written here. Okay? Here it is written that the probability density of two joint events is the product of the two separate probabilities. It is an hypothesis of independence, is even stronger than hypothesis of no correlation. Independence implies no correlation. Okay? So, he says, but look, what kind of correlation or dependence can particle 1 have on the remaining n1 minus particles? If they are 10 to the 19, and they move very randomly, forget about the fact that the dynamics is deterministic, because I told you, right? When there is this much, the dynamic is deterministic, but you end up placing particles randomly in space. So he says, but let's be honest and realistic. There is no chance that particle 1 remembers having collided with any other particle. So it is reasonable to assume the independence before they collide, because after collision they will be correlated, but before they collide I can factor it out. This is called hypothesis of molecular chaos. Now you take this ansatz and you substitute it over there and you get the Boltzmann equation. And this is one of the most important equations of physics, which has an incredible amount of applications with variations, okay, with variations that go from hard physics, like electrons in metals, and it has quantum mechanical versions and there are relativistic versions, to the description of crowds, for instance, to the evolution of tumors, to the flow of blood, of red blood cells in capillaries, to you name it, and you will find that someone has applied the Boltzmann equation. Of course, if you take it too far away from the realm where it was derived, there is no guarantee that it works. but it works in so many instances, okay, that people like to use it even when it is not guaranteed that it will work well. Can this thing be justified? Which gives us an idea of when it is legitimate to use it or not. Now, the story would also be relatively long, but I make it short for you, and then we stop. It works under a limit that was developed more than 50 years, maybe 60 years after Boltzmann had devised his equation, that is called the limit of Boltzmann-Grad. Boltzmann-Grad limit. When is it really legitimate to factor out F2 as a product of 2F1? Under these conditions. You have n particles which have a cross-section sigma squared. You want this to be a constant bigger than 0. Because this means the particle can collide with each other. If they do not collide, if they were points, if sigma squared was 0, if they were points, they pass through each other, and there is no reason that they distribute themselves uniformly in space. The distribution in space is due to the collisions. You see? If you throw a ball and it doesn't hit the other ones, you are not going to cause any disordered situation. It's the fact that you collide with them, and then the next one collides with the other, and the next one collides with the other, and because they are spheres, they are strictly convex surfaces, there is an effect of defocalization that makes distances expand and fill the space. If I have one particle that comes through here, it will go out through there. But if it comes a little higher, it goes that way. So what was a short distance has become, through a collision, a large distance. And because the billiard is finite, increasing distances, sooner or later, you will fill everything. So you want collisions to be present. But you want particles not to hide each other from collision. So this is your particle 1. If I have the particles are distributed like this, you see that my particle cannot collide with all the n-1 particles, because if I hit this one, I cannot hit that one. But if instead of having bolts, I have something tiny, then this one in front cannot hide the other one behind unless they are through a set of 0 measure, but then it is a set of 0 measure, that they are exactly aligned. But that will almost never happen. Okay, so you want your bolts to be small, and being small, the volume will be small. Okay? But if you take this, look what happens. We have that sigma squared is equal. Goes like 1 over n, okay? It is order 1 over n. That means that sigma is order 1 over root n. What is the volume occupied by the particles? Volume is equal to n times order sigma cube, okay? Because sigma squared is the area, sigma is the diameter, sigma cube is the volume of the sphere. But n sigma cube is n times 1 over n to the 3 halves. So this is order 1 over n to the 1/2, if you can read it. What does that mean? It means that if particles are many but small, you can have the collisions remain, but the volume they occupy is 0. So the factorization makes sense, okay? And then you are describing a rarefied gas, a gas in which the volume occupied by particles is negligible, but of course particles are so many that they still find a way of colliding with each other. So there is chaos. And again, factorization makes sense. This is the Boltzmann-Grad limit, okay? That you take n to infinity and sigma to 0, but in this way. In such a way that n sigma squared is a constant. So this justifies the Boltzmann equation. Now, you do not imagine how much mathematics is behind what I've just told you. Okay? There are, in particular, the Italian and the French school, but in recent years, mostly the French school, who have written books and books and books to come to the end of this story, and the story is not finished. Okay? The story is not finished. There are still questions to be solved in general and so on. I think I will stop here. Ah, I finished my time. Yes. Well, we have the tutorial for questions. We have because we have 2 hours now, right? Okay. So, yes, I stopped. I apologize. I didn't realize that it made long, but hard to make it short. Is it okay? So now we have a break. 10 minutes break, then we go to the lab. Okay, so keep all your questions and doubts and curiosities and whatever you like to know for the next 2 hours. Okay? Thank you very much for your patience. You've been very good. And see you in 10 minutes. Or maybe even before. There is tea? Is there any tea?
Yes, yes.
There is tea. Then.